Hello, everyone. This is day 3 of our 30 days, 30 deep learning projects challenge. So, let's get started. Today, the problem is to explore back propagation theory and peak learning rates using MNIST. So, the flow is going to be same. We will go and take the help of ChatGPT, ask questions to help in give the full code, and whenever I'm going to see any new term that I don't understand, I'm going to ask from the chat GPT. So let's get started. I'll say, hey, can you, hey, today is day 3 and here is the problem. So today we will be exploring the back propagation and learning rate. Hmm. So let's wait. Maybe I can go and move this thing a little up here. Yes, so let's get started. So it says that is great step forward. Today's we are diving into the core mechanism behind how neural network work, back propagation. We'll also experiment with learning rates to see how they impact training using MNIST dataset. I will make sure to explain this concept okay. Now, what is back propagation? Backpropagation is the algorithm that makes neural networks learn by adjusting their weights. Especially, it's the learning process. Okay, it works by calculating the error in prediction. The difference between the predicted error, we all know that it is the difference between the predicted value and the actual value, and then propagating this error backwards through the network to update the weight in each layer so that the model can make the better prediction in the future. I do understand a little bit, but not that much. It what is trying to say is that it is a learning process where it adjusts the weights, and by doing that it calculates the error and keep on improving, having the minimum error is the error in the prediction is the error, the difference between the predicted value and the actual value. So how does it do it? In simple terms, forward pass. How back propagation works in simple terms? Forward pass. The input data is passed through the network layer by layer to produce an output. Okay, the input data is passed through the network. Okay, layer by layer to produce an output. Okay, the output is compared to the actual labels to calculate the loss. The output is compared to the actual label to calculate the loss. That's, yeah, we know. Backward pass. The loss is used to compute the gradient of the error with respect to each weight. Okay, and the weights are, yeah, and the weights are updated in the direction that minimizes the loss using the gradient and the learning rate. So it uses this and adjusts the weight such that we get least error or least loss. Then how does it what does it do? The learning rate controls how big of a step we take in the direction of minimizing the error. Learning rate, for me, I guess it is how much of a difference we assume. I mean, moving towards, if we increase or decrease the weights, how much should we decrease the weight so that we move towards minimizing the error. So high learning rate, faster learning, but might overshoot the minimum, miss Convergence, correct. Why we might miss opportunities. So high, but the model will be trained faster. Low learning rate, more stable, but can be slow and get stuck in local minima. It can be slow with low learning rate, but stable, right? So today we will experiment with different learning rates, okay, and to see their effects on training. I will go, and I still have not understood about the back propagation. Um, but let's go ahead and read a little, and if I will not understand, I'll go ask from ChatGPT again. Load, okay. MNIST data we are loading. We have the same images that we saw on day two. We normalize it. The images are from 0 to 25 to 55 pixel value, so we will normalize it between 0 to 1 so that they remain in a shorter scale. Then we build a sequential model, train it. First, we flatten the model from 288 to 784 vector, and then we add the first layers, and then we are going to have learning rates as 0.01, 0.001, and then 0.001, which is too small. And then for each learning rate, we are going to compile similar rate. So if you remember, yesterday also we did similar thing, but today we are exploring with different learning rates. So yeah, compile, optimizer, loss matrix, and then compile. For this learning rate, here we are specifying in the atom that the learning rate is this. Print the learning rate, then we fit the model, and then we save the history for plotting in this history dictionary. And then so we have this and then this, so we will see what it will produce. Visual, okay, visual also we will print all this from the history dictionary. The loss of training and validation data from all the epochs, and then we will see the accuracy. But I do the code, but I still don't understand, uh, did not understand much of that propagation, right? Can you please give an easy example? Yeah, let's understand back propagation. I have the confidence. I would not even require to look at the code. I can go and understood that what we have to do with the respect of code. We just have to explore with multiple learning rates and specify it in the where specify it in the atom optimizer that this is the learning rate. Otherwise, everything is same that we did yesterday. But what is this propagation? Let's understand it again. This is the learning process in neural network. That's we have understood. Essentially, it is the way the network adjusts its internal parameters. That is based on how wrong it was in predicting the output, in order to improve further prediction. To understand back propagation, imagine a team of chefs working in a kitchen. I will walk you through the analogy to make back propagation more approachable. Okay. So we have to imagine that we have a team of chefs working in a kitchen. Hmm. Let's imagine you are with a team of chefs who are trying to cook the perfect dish, and your role is to taste it and give feedback. Okay. You want to help them improve each time they try. Okay, similar to how backpropagation helps a neural network improve its prediction. So our job is to taste the dish and then give feedback so that the team of chefs can uh, perfect the dish. Can perfect the dish. They can gradually improve based on the feedback I provide. And Chat GPT says that this is how back propagation works. Similarly, so let's understand. Forward pass. It is that the chefs cook the dish, calculate the error, you taste the dish and then give a score. Propagation. Chefs adjust ingredients. Okay. Chefs do what? They adjust ingredients. Okay. We give feedback, sending the feedback back. They adjust ingredients. They update the ingredients, learning and improving the dish. And then again cook it and then calculate the I taste it and then I give the score. They adjust the ingredients and then improve the dish. In the neural network, a forward pass means passing the input through each layer until it reaches the output layer. A forward pass is passing the input. So let's open a neural network. So this is a typical neural network. So this is a forward pass. This is a forward pass. Then it calculates the. So forward pass is passing the input layer in until it reaches the output layer, and then I taste the dish. After the forward pass, so forward pass is the complete process from input to output layer. Forward pass is the complete process from input to output layer. And then we have this you taste the dish and give a score. In the after the forward pass, we calculate the error. We calculate the error as in I taste the dish and then give the feedback. So in neural network, here it calculates the error as in the difference between the actual value and the predicted value. Okay, and in the next step, propagation. In the error is used to calculate how each weight in the network contributed to the error. These weights are then updated to improve. Okay, in the propagation, what it does now, it the output is produced. It has also calculated in the second step the difference between the predicted and the actual values, that is the loss. And then based on the loss, using the back propagation step in that phase, it updates those weights. It does what? It adjusts those weights that have contributed to that error, and then hence the improve the outcome. Okay, and after giving the feedback, each. So what it does, so I have this query. Here also these weights are then updated and to improve the outcome. If the weights are being updated here only, then in the step number 4, which is weight update. Okay, in the back propagation, calculate how much each weight contributed to the error by using chain rule. Okay, so in the back propagation, it is evaluated. It is in this phase, each way it in this phase it is being evaluated that each how each weight contributed to the error by using the chain rule. And then in the fourth step, the weights are updated accordingly to reduce the loss for the next forward pass, and then it goes again. Okay, so here we'll explain in our simple term. In the first step, it goes to which is the step of forward pass. In forward pass, the f- uh, I mean it goes from input to output layer. through each layer, and then produces the output. In the second layer, it calculates the loss, that is the difference between the predicted and the actual value. In the third step, it back propagate, which is it finds out how much each weight has contributed to that error. And then in the fourth step, it updates the weight, it adjusts or improve update the weight, and then is ready to go to the forward pass again, for again doing this, repeating the same four steps to minimize the loss. So this is what back propagation is. So it corrects mistake gradually by tweaking the weights. It helps the network by improving itself through iteration. Each time it learns a bit more about what adjustment need to be made to reach to the ideal output. Now I understand. Over time, it leads to a model that has learned enough to make very accurate prediction. Okay. Now gradient descent. If you remember, we have explored descent. So gradient descent is a kind of a slope, uh, right? So gradient descent is kind of a slope. If I'll go, this is a gradient descent. Here the loss will keep on decreasing. That's the main motto, right? And after some point, they will have the minimum loss, and then it will increase again. So this is what we have to find out in the back propagation. Okay. Okay, and then what is the learning rate? Learning rate is how much we should update, by how much value we should update the weights. It's like the size of the step you take when walking down the slope. Large steps might get you there faster, but you could but could make you miss the target. While small steps are more cautious, but can be slower. Yeah, understood. I understand. So let's go and start building. I'll do what? I'll create a Python file for day 3, add to our Git repository, mention what the problem is. The problem is this, and import the files. Import numpy as np. Why we are going to use it? We are going to use it to do mathematical operations. Then import pandas as pd, because I want to see how our data looks like. uh, Panda is great at visualizing the data using data frames. Import from TensorFlow keras dataset. Import uh, MNIST from TensorFlow keras models. Import sequential from TensorFlow keras layers. Import dense layer, and then a flatten layer. Flatten layer is to flatten the images. If you remember, yesterday also we saw this dataset, and then we saw this data. These are the images of 28 by 28 size. And then we, since the neural network understands only 1D array, so we have to flatten it into 28 by 28, which is 784 size vector. So we will do that using this layer, and then we will draw plots as in graphs to see how the accuracy and loss are looking like. So we have to import this. Now we will do what? We will load the data. which is x train x. So we'll do what? X train x validation. This is y train. Hang on, my watch. Okay, x validation, y validation, and then we have MNIST load data. Okay, once done, we will do what? Normalize it. Normalize the data to range 0 to 1. With initially it is going to be in the range of 0 point and 0 to 255 because it is an image, so we have to normalize it. X train is going to be x train divided by 255.0, and x validation divided by 255.0. Now, why we are not doing for our y train by value? Why? Because they are single digit data, which is to tell what the number is in that image, whether it is 1, 2, 3, 4. So it is always going to be in the range of 0 to 1. It is a category. So we do not have to normalize it. These are not the features. Now we will do what? I want to see the data, right? So what I'll do, print, I'll do what? X X train data frame, pd dot data frame, X train X validation data frame. Let's see how the target is looking like. We will do what? Data frame, not data frame, it is going to be a series because it is going to be a one d vector. So it is going to be x y train. The label is going to be label. What do you want to label it? The number, and print x train data frame, and don't print it. Just print the head of it. Y train head. Let's come here and run this day 3 file, and we have error on line number 18. What error do we have? Label. This is, yeah, this was the argument. What did we have? So this is not doing what? Let's do what this. I'll tell you what the error is. Okay, I have to comment this, clear this. Let's run it, see if this is working fine, and then I'll tell you. See, we see the first 5 rows as first row, first image is 5, first second image is a digit 0, third image is a digit 4, fourth image is a digit 1, and fifth image is a digit 9. So this is working fine. Why was this not working? Hang on, I have a mosquito. So this was not working because this is in the, so let's do what. I'll tell you why this is not working. So I'll show you the shape of it. It is into 60,000 rows images, and they are of 28 by 28 size. So we have to do what? We have to flatten them to visualize it before. So how am I going to flatten it? Flatten it, the image into image, uh, 28 by 28 pixel image to 784 vector y, one dimensional vector. Why? Because neural networks, they work with one dimensional vectors only. So why we are, so what we have to do, we have to do this extreme flatten, uh, flat, and we are going to do extreme dot reshape. Is that what we did yesterday? Yes, sorry. uh, Reshape, yes, we want to reshape, and we want to reshape from 2828 to 784. So here we say 28 to 28, and here we should pass this flatten 784 one dimensional vector. And when we will do that, let's see, uh, data frame this. Yeah, better. Now we should be able to see it. It should work now. Oh, we have an error. So this was the error. Now it should work. So why was that working? Extrain dot reshape minus 128 by 28. Oh, sorry. It should be reshaped to what size? 784 size. Now it should work. So yeah, see, we have 784 columns, and this is how they are looking like. They're looking like in the floating point values, range from 0 to 1. And why we are doing it? Because model will train it faster. The range is smaller now. Now, yeah, so this is how the data is looking. We can simply go and visualize it, the X validation also, but it is going to look like this only. So I am going to skip it. I'm going to do what? I'm going to skip it. Okay. Now I'll do what? Last day, I mean yesterday, we flatten it like this before passing it to the data frame. Today I want to do it with the flatten layer. So I'm commenting it for that reason. Now now we are going to build the model. Okay. Model is sequential model, and then add the layers. The layers is model dot add first layer. We are going to add the flatten layer, and the flatten layer, the input shape in this flatten layer is going to be 28 by 28. Yes, the input shape is 28 by 28. Next layer we'll have a dense layer, and dense layer, how many neurons we want? We want 28 neurons, 128 neurons. And we want, why 128 neurons? You must go and see the yesterday's video or I can explain it here by. So when if you these numbers in these layers are usually in the power of 2. This 128, 256 are very 128, 64 are proven to be very good as starting point for training the model, neural network model. We can obviously go further and decrease it further, but for starting this thing, the training of the model, we can start with 128 and then minimize to a previous power to uh, uh, power to value, which is 64, and then we will print the output, which is 10. So let's do that. The activation function, we will go with rectified linear unit. And the input shape, we do not want to specify the input shape here. Earlier, if you remember, we did specify the input shape here for this layer. Why are we not specifying it here today? Because input in the shape of input is usually specified in the first layer only, and then in the further layers the input shape is calculated by the output of the previous layer. So the output of this previous layer is what? 784. So this will go into this as the input layer, so we do not have to explicitly specify that. Now mention the next layer. Add dense. Next layer will be 64. Activation function will be rectified linear unit. And then we'll have the output layer. The output layer will have how many? 10 digits, because we want to categorize, we want to see what type of a number it is going to be. So we want to have the probability of each number, as in what this image resembles to, whether it resembles to 1, 2, 3, 4, 0, 5, 7, 8, 9, 10. it, Sorry, 10 we don't have. So to see the probability, we first, how many inputs, type of inputs we have, how many possible type of outputs we have? 10, 0 to 9. So that is why 10 here in our output layer. And then the activation function is going to be different. Again, it is going to be softmax, which is used to output the probability, and the sum of the probability of those 10 neurons is going to be 1. So whatever neuron is going to have the maximum probability, that is going to be the predicted value, that is going to be the predicted number for that image. Okay. uh, yeah. Now we'll do what? Compile the model. Mhm. But for that, what we do? Experiment with learning rate. So, learning rate, let's create a list. Learning rate is 0.1 or 1, 0.001, 0.0001. Okay, this is going to be our learning rate. Sorry, this is learning rates. And then we are going to do for I learning rate in learning rates. What we are going to do? And then we are going to create a dictionary also. Store the training history for each learning rate. So history of learning rate is a dictionary, and here we are going to store everything. So here what we are doing, model dot compile. We are going to compile the model. We are going to compile the model on what? Xtrain. Sorry, not fit. Here we specify three things. Optimizer. Optimizer is going to be tensorflow.keras. Optimizer Adam. And here what I want to do, I want to import it. I don't like this from import Adam, and we are going to call this, I don't like mentioning everything once, Adam. The learning rate is going to be this from this loop. Then we have loss. Loss is going to be a sparse categorical cross entropy. Why? Because it is a sparse, that is 0 to 9 digits, not one hot encoded categories. Then we have categorical, we have to calculate this category. The data is of categorical type, so we have to go ahead with that calculation of loss. And so yeah, so sparse categorical cross entropy, CROSSENTROPY. And the metric to for the performance evaluation is going to be what? It is going to be accuracy of the model is being used to calculate the performance. Done. Now once we have compiled, we have to do what? Train the model. And training of the model, we'll say what? We have to print first, and it will print training, because we it will output as verbose, right? Whatever epochs it is training on, so everything it will print on the terminal. So we'll say just a line with training with learning rate. Okay, now we'll do what? We will store this in this history variable. What? This training. So we will train the model on x, train x, sorry, y train. The validation data is going to be on, so when we will pass, it will first flatten it, right? So it will have x validation, y validation, and then how many epochs we want. Yesterday we saw it was doing very good, predicted everything almost, I mean with accuracy 96% yesterday I'm talking about. So we'll go ahead with 10 epochs. Let me see what it is doing today. Yeah, 10 epochs. The batch size is 32, and we want to see whatever it is, however it is training the loss and everything for each epoch. So we will do with verbose 1. Once done, we will save the training info in the history dictionary. So history lr_lr dictionary, we will store this lr for this learning rate. This is going to be the history. Okay, now once done, we will do what? We will plot the graph. We want to plot the graph. Okay, so let's write the code and then we will run it all together. We want to plot what we want to plot. We want to plot the history, and then sorry, we want to see the loss for our training and validation data. We want to see the accuracy for our training and validation data across all the epochs. So let's do that. For before that, let's define the visualize the training and validation loss accuracy across epochs for learning rates. Okay, so we'll do what? We will do create a plot of, create a figure of fixed size is going to be 10, 14 is to 8, too large, but let's see what ChatGPT is doing. For learning rate in learning rates, we are doing what? We are plotting a graph of, okay, history learning of this learning, the loss, sorry, the loss of our training data, label, not lambda, label, right? Label is going to be, label is going to be training loss of this learning, training loss of learning this. And then we will plot, not cool, plot the validation, the loss for our validation data, validation loss. Earlier we saw for the training data, now we are going to see for the validation data. And then we'll do what? Spelling typo, TRAIN. Validation loss is going to be LR, and then it will print all the plots, and for all the plots the X label is going to be epoch. No, for X label is going to be epochs, Y label is going to be loss and validation, training and validation loss, training and validation loss. And the title of this graph is going to be training and validation for different, sorry, this should be, and it is loss, no, so let's go ahead with loss, training and validation loss for different learning rates. Okay, let's plot the items, as in which curve is represents what, and then do what, show it. Once done, we are going to replicate the same. Now visualize, we are going to visualize this what, earlier we visualize the loss, now we are going to visualize what, we will visualize the accuracy. So here we will say accuracy, and then we will accuracy for training, accuracy, everything is going to be same, just change loss with accuracy. The graph is between accuracy. So yeah, so yes, let's go. This is looking almost done, so let's clear it and run the code and see what it is going to print. And we have the error on line number 44. Learning rates will be, let me see if I'm making any typo here. Oh, this is the correct argument name. I had a typo in this argument. It should be learning rate, not learning rates. So we can see that it is training for learning rate 0.01, and this is how it is training. The first loss for first epoch it is 0.25, gradually decreasing. See, accuracy is gradually increasing. For now it is training for the 0.001. See, the accuracy is was way better for when we had this training curve. Loss was 2 minimum. Here the accuracy was 0.99. Here the accuracy was 0.9, sorry, 97%. When we had the learning curve as 0.0001. So let's see. And so it had 99.65, it had 99.54. So we see the loss is even further. The more we are going, so we see the best model we have trained so far is with the learning curve 0.0001, right? So let's see. The loss is, this is the loss in epochs. For the loss for let's see this. Training loss for 0.0 and validation 0.01. This blue and this orange. So this is going like this. Here the validation loss increased here, and then decreasing, and the trailing loss keeps on increasing. It should also have increased, decreased, right? Then the training loss and validation for 0.001 is green and red. So it started increasing here for validation. For validation, it was not working as good. Let me see. For validation, was it working? Let's monitor for validation. 0.17 increase. If it increase, decrease, increase, decrease. Here it was static. Yeah, it is slowly increasing here. So it started with lower and then validation it increased. For unseen data, the loss increased. Yeah, and here for, yes, that's why it is increasing. And for training and validation loss for 0.0001 is, this is the validation loss increased. And yeah, so for unseen data, I think this is working better. This is working better, the first one. Hmm. Here the loss was maximum. See, the loss was maximum when we had this training data rate of 0.0001. The loss is like increasing. It ended with 0.23. Here it ended with 0.198. Here it ended with 0.15. I would rather go for this one. Training with learning curve 0.018. So I'll go and take this screenshot. And accuracy, let's see accuracy also. Accuracy, we saw that the accuracy was getting better with minimizing the the slow learning rate. The slower the learning rate, the better the accuracy is. See, for 0 point, for first one, blue and orange, so the accuracy is increasing, very good for both validation and training data. For 0.01, the training is green, validation is red. Training is green and validation is red. It was almost static, the accuracy. It increased, but it became stagnant here. And then for training accuracy and validation accuracy for 0.0001 is this violet and brown. See, it is like stagnant, not changing, stagnant. So I feel here they do not have much difference. So I feel it is kind of overfitting situation. I feel for our problem 0.01 is the best solution. So I'll do what I have coded the application program, and here, here is the output output plot. Which learning rate do you think is good. So I'll go attach both the plots. I can simply copy paste the epochs output as well, but I think I just want to see how ChatGPT is going to evaluate this image, because it does great evaluating and reading the images. So conclusion: the learning rate of 0 point seems to be the best option. Smooth convergence, training validation loss both decreasing steadily without fluctuation, which shows a stable learning process. Okay, so if I'll go here, loss is decreasing steadily. Validation in this, it is decreasing 0.4, 0.3, 0.1, and decreasing to 0.01. Loss, and here the validation loss is 0.14, steady, increasing. The validation loss increased actually. Acha, okay. High accuracy, training and validation accuracy both improve steadily, indicating. Okay, good. So the steadiness is there in 0.01, 0.001, this one. 0.01 is too high, leading to fluctuation and inability possibility due to model overshooting. Okay, yeah. So the fluctuation was too much. From, oh, loss fluctuation was too much. 0.25 to niche, to down 0.16 to over 0.15, 0.3, 0.10, and then decrease to 10. But the validation was increasing, so there was no steadiness here. See, 0.19 to 0.15 to 0.15 to 0.15, and then increase to 1.8, 0.18. So there was no steadiness. For steadiness, it is saying that 0.01 is better. Okay, and 0.001 is too slow, resulting in slower conversion. The model not effectively training with the given. So 0.01 is the best balance between the speed and the. Okay, speed. So let's do what? Let's mention it here and conclude the day. So we saw that 0.001, 0.001, the middle one was working was better here because of the steadiness in this fluctuation. It was not fluctuating too much as we saw in 0.01, and it was not too slow as we saw in 0.0001. For steadiness and smoothness, we are going ahead with 0.001. So let's do what? Let's add this day 3 code to our repository. Add code for day 3 to our, push it to our main branch. Let's go to the repository and see the code is here. So yes, you will soon see the post, as in the textual post on this text journal, and this video of me doing it live, sort of my development log on the YouTube channel. So thank you very much.